Hello friends, welcome back to my channel and thanks for watching my previous videos and the good responses. Once again, good morning, good afternoon and good evening. As I committed, let's start with the new learning and let's start with the new topic. So today I'm gonna talk you on the simulation. Today's simulation is arguably one of the most multifaceted topic in the industries. It can also be one of the most important topic to corporation as well. As you know that simulation is widely used in everywhere, regardless of the industry type. It is being used in the automotive industry, used in the medical industry, pharmaceutical industry, telecommunication industry, and the aerospace industry. So, but the still question is there, why simulation? There are multiple reasons to use the simulation in the product life cycle development. One of them, or the few of them, are most important is the time. When it comes to the time to market or bringing one of the product early to the market, the time is very important factor. Simulation helps very aggressively here. It saves the time to develop that product with the help of their mathematical equations. I will take you through in details why simulation, but when it comes to most important topics or most important points, the time is one of them. The second one is the cost. Cost to the solution is very important, because just imagine you are investing of multi-billionaires to develop the product, manpower, to develop many manpower to develop the product, but simulation is the single tool which can give the result in very less time with a very less price. The time is very important, cost is very important. And third point which I gonna talk you is the test where the human being is facing the life-threatening poisonous environment. So simulation helps you over there. It helps you to have the testing done on the product with the poisonous environment without threatening to the life of one of the operator. So these are the most important key points to bring the simulation into the market. So let's talk about the different types of the simulation. So I'm gonna talk you today on SIL, MIL, HIL. So software in loop simulation, why it is used, where we can use, how it is used. When it comes to model in loop simulation, why it is used, what are the advantages over the other simulation types, and what is the hardware in loop simulation. So let's start in the detail. Friends, today I'm going to talk you on simulation techniques. Sometimes I refer this as a simulation methods as well, testing methods. But before going into details, let's see what is simulation and why it is used. What are the different simulation tools? Today, I'm not going to talk more in details about the different simulation tools or the competitors or the players in the market, but definitely while going through the different slide, I will touch base to the different competitors which are in the market. Then we'll see the software and loop simulation in detail, then model in the loop simulation in detail, hardware and loop simulation in detail, and finally while going through all these SIL, MIL, and HIL testing methods, I will take you through the use cases as well. But before jumping to this testing methods, simulation techniques, uh, we'll start with the history. History is very interesting. It started in the World War II. It is, or I would say, it was a global conflict in which started in 1939 to 1945. The history of the computer simulator or the computer simulation dates back to the World War II, when two mathematicians, John von Neumann and Stanislav Ulam, were faced with the puzzling problem of behavior of the neutrons. So this is what the simulation history, or it is backed in World War II. Hit and trials experimentation were too costly and the problem was too complicated for various analysis. Hence, the Rowlett wheel technique was suggested by the mathematician, and the basic data regarding the occurrence of the various events were known, into which the probabilities of the separate events were merged in a step-by-step analysis to predict the outcome of the whole sequence of the events. So relate wheel technique is very well known to everyone. With the remarkable success of the techniques on the neutron problem, it soon became the popular and found many applications in the business and industry. So post-World War, when new technology developed for a military purpose during the war,
began to emerge a new problem solving tools in the world at a large. So this is what the history was. But when we look back in early 1980s, there were common problems as well for the simulation as this technique was completely new. Simulation was extremely complicated and so only expert can use it. That was the trend at the time in the early 1980s, sorry. So simulation takes forever because of the programming and debugging. So it was taking too much time for doing the programming and the debugging. That were the challenges. But the entire world um, just came up out of these challenges, and today that simulation is used everywhere. Every industries the simulation is widely used. So before jumping, let's start with the definition. So definition is very simple. When it is comes to the simulation definition, simulation is the imitation of the operation of the real world process or the system over a time. So over a time is very important. So when we define one of the system, we have to see its performance over the time. So simulation requires the use of the model, and the model represents the key characteristics of that system. So it requires really to have the mathematical model, and that mathematical model represents the key characteristics or the key behavior of that selected system. So simulation represents the evolution of the model over the time. As I explained, we have to see the performance of that system over a time. This is what the definition of the simulation. Now, still the question comes, why simulation? There are multiple reasons behind the invention of the simulation and the need of the simulation. Out of that, I have listed a few of here. When it comes to the time to resolution, just imagine instead of looking for the cost of the product, it is always important the time to market. So simulation gives you a very less time to find the resolution over a problem. So this is the beauty of simulation. Time to resolution is very less compared to the actual testing or manufacturing the actual product and bringing to the market. Simulation gives you the virtual environment to replicate its mathematical representation of the system and see the performance of the system. The time to resolution or the time to market is very important factor when it comes to why simulation or what is the need of the simulation. Second factor or the second driving parameter is the cost. It is very cost effective solution. Just imagine if you wanted to develop or manufacture one of the product, you are investing a lot of funds, investing a lot of manpower. It costs a lot to the manufacturer. So simulation saves your more cost. You just have to buy one simulation tool and simulate the mathematical behavior of that system or the statistical behavior of that system. That's it. It saves a cost as well. So time to market, cost effective solution, and the last one is the safe operation. Just imagine if you wanted to perform any of the system test actually on the system in the poisonous environment, it is life threatening to the operator. So simulation avoids such types of operations and it is allows to the operator to do the testing on the virtually on the system. So this is very safe to the operator, and this is the major driving factor behind why the simulation is required and what is the need of the simulation. And it solves the real-time problem, real-time world problem. It gives a quick and clear insight into the complex system, and very important is the portability. It's very portable from one system or the one PC to the another PC or one computer to another computer. You can just shift your simulation tools, simulation software, and you do the simulation. These are the key major parameters or the factors which drives why simulation, what is the need of the simulation. Till now, we just have covered the history, which history was started from the World War II, and then there was a lot of revolution happened over the simulation. All the industries, starting from the automotive, aerospace, pharmaceutical, telecommunication, everyone started adopting the simulation technique to save the time, cost, safe operations, quick resolutions over the problem, and the portability. Now let's start jumping to the main topic, that is SIL, MIL, and HIL. So as I mentioned, SIL is a software in the loop testing method. or a simulation method. And this SIL basically um, it compiles the generated source code and execute the code as a separate process on your host computer. I'm repeating again here. What SIL method does or testing does or simulation does this method, it compiles the generated source code and execute the code as a separate process on your host computer. By comparing normal and SIL simulation results, you can test the numerical equivalence of your model and the generated code. So that is very important when it comes to uh, software in loop simulation definition. And the next is software in the loop is a method of testing and validating code in the simulation environment in order to quickly and cost effectively catch the bugs and improve the quality of the code. That is also a very important factor. The next point is the term software in the loop testing or the SIL testing is used to describe the test methodology where executable code such as algorithms or even an entire controller strategy usually written for a particularly mechatronic system is tested within the modeling and environment that can help prove or test the software. That's very important. And the last point is software in the loop is a method of testing and validating the code in the simulation environment. So just remember, testing and validation of the code, of the source code, whatever the source code you are developing from your algorithm, your control strategy, it helps to validate that code in the simulation environment in order to quickly and cost effectively catch the bugs and improve the quality of your code. So fixing up the bugs, quick checks on your code, improve the quality of your code, software in the loop simulation technique or the testing method is widely used. Typically, SIL testing is conducted in the early stage of the software development process, while the more complex and costlier technique that is called hardware in loop simulation that is being done in the latter stage of the product development. So till now, we have just discussed about the software in the loop. You just have to remember that it is for testing and validation of the code in the simulation environment in order to quickly and cost effectively catch the bugs and improve the quality of your code. So if you see mm, in pictorial presentation, here is your uh, controller representation in the binary file. If you are using the MATLAB, you can generate the S function out of that. Here is your plant model, which are in the Simulink. Now I'm talking here the Simulink, but you can even use the AMECM, you can use the LabVIEW. These are the players, these are the tools, different tools, which can be used for SIL, MIL, as well as for the HIL. So I'm just referring here the Simulink. So here you are simulating your plant inputs and outputs required. You can simply put the mathematical equations, some integration, differentiation, whatever the output of that plant model, which directly goes to your code. Suppose you have some code which are in the compiled form in the binary file. You fed that input to that code, whatever the inputs you are required in respect to testing your code. And again, you fed that to the plant model to observe the performance, how it is behaving, what are the different signals going on and all. So you can do that in plant model. So you can put different probes and all everything here. So in very short, it gives the compiled application and you can have the simulation at very early stage and it is in the accelerated simulation form. You can very fastly you can simulate your performance of your code and check and debug the code performance. It's low cost and short development time, and it's a non-real time response. It is not a real time response because you can set up the model's execution time as per your need. You can go very fast, you can go very slow. It is purely dependent on the way you want. But as I'm referring here, this is not the real-time response. But this technique is widely used for looking for the initial checks in your code as well as to check for bugs in your code, which are in binary file or in the C file. So in very simple, if I look both this controller binary file as well as your plant, which you have simulated uh, with the different inputs and the output are on the same host PC. So I can only use a MATLAB Simulink, or I can only use a LabVIEW, a National Instruments LabVIEW, or even I can use only AMISIM software where I can put plant. I can use S function for the C code, which I wanted to check. I fed the inputs from this plant model to this C code, and I fetch the output out of this C code, which I wanted to evaluate or which I want to test. And I can view that parameters here on the scope. So this is how it looks in the model. This entire model runs on the host PC. No need to use the multiple PCs or the multiple software. That is the beauty of this SIL. So let's jump for the next topic, that is the model in the loop simulation or the model in the loop testing. So this testing is also called MIL testing or the model testing. It is the testing of single or integrated models in the model-based development environment, such as the MATLAB Simulink, NI LabVIEW, or AMSC, or ASCET from ITAS, ASCET from the ITAS. So these are the different simulation tools which can be used. So one of the significant benefit of the MIL testing is that it helps in improving the quality and efficiency of the model. That's very important. And when it comes to the model in loop testing, to verify the accuracy and acceptability using the plant model of the control algorithm, software in the loop to validate the behavior of the generated C code used in the controller. So model in loop or MIL, the whole system is model. Here we model the entire system. So it's possible to simulate a complete environment where you can talk about the vehicle or where you can talk about any product in order to test um, the complete behavior of the system before prototyping or manufacturing that entire function for the validation. And the last, when I talk about the block diagram, here is a controller which are basically which are running in the Simulink. And here again, your plant mod where you can feed input and output. And in the controller, you have entire your algorithm written in the state flow or in the Simulink or in the virtual interface in the lab view or in the AME sim. So here you simulate the entire controller and you feed the output of your controller to the plant model, whatever the model you want have simulated here. Again, the output of that plant model fed back to in the control loop to the controller. So few highlights. It is purely simulation. You need to have the simulate entire controller as well as the plant. Then this is the proof of concept and design for the optimization. It simulates the various scenario and identify the potential issues in your controller or in your algorithm. But again, a very important point is that again, this is not the real-time response. You cannot get the real-time response from the actual system, but the results from this type of testing, it goes about the very up to the very highly correlated results. So you can check the interlocks of your algorithm. You can check the malfunction of your algorithms. That is easily possible with the help of this MIL technique. So MIL means model in loop, and it's a method to test the entire model. Earlier we talked about the SIL, and in SIL we check the code, C code or any binary file we check over there. But here I'm talking about this method is to talk about the testing the entire model. First, you have to check the model is working fine or not without having any error. So you need to send the input signal. As I said, you need to send the input signal to the model and take the simulated values out of that to view the performance or to figure out the issues or something like that. So compare simulated outcome values with the expected values. If these two values are matching, then the MIL is success, else it is failed. So again, this technique is widely used whenever there is a need to check the entire algorithm or the controller logic. If it is in the written in the Simulink or in the LabVIEW or it is in the AMSIM, you can directly pull that. Sometimes you do the course simulation as well. If you are running your entire model into Simulink, you can pull the AMSIM model as well here as a S function and creating the library, and you can feed the input and output to this plant model and check the performance. So again, very important part is that here also everything runs on the host PC. The definition for the host PC is here, the computer or the PC or the system where you have installed the software, Simulink, LabVIEW, or AMSim. On the same PC, on the same single executable file, Simulink file, you can run this entire model and check the performance, how it is performing, how the model is behaving. Everything is possible inside the single file. Now, when we see the snapshot from the model, if this is the MATLAB Simulink model, here is your plant. You can have the input output, you can mux demux the signal, you can put the probes, you can do the simple mathematical calculations of the equation, feed that inputs to your controller through some conversion blocks. If the data type is required in the single, required in the bits, required in the double, that way you can convert and feed to the controller. So inside the controller, your entire algorithm is there. So SIL, MIL, both techniques are clear now. Now we are jumping into the next topic, that is hardware in loop simulation or hardware in loop testing method. So hardware in loop simulation is the technique for validating your control algorithm running on an intended target controller by creating a virtual real-time environment that processes or control that by creating a virtual real-time environment that represent your physical system to control. So it is a technique where real signals from the controller are connected to the test system that simulate reality, tricking the controller into the thinking it is in assembled product. That's the beauty. In hardware and loop simulation, you fool your ECU that it is actually connected to the vehicle or actually connected to the product by simulating its environment. Environment means just you are simulating its input and output. If there are few sensors, you simulate that sensors with the help of real-time simulator. So real-time simulation and results are more accurate when it comes to comparing the SIL and ML. This is a real-time simulation result, and these results are highly accurate, and it is completely equivalent to the actual system performance. So HIL testing are executed with the final issue software and designated target hardware. The environmental of the ECU or the environment of the ECU can still be simulated. However, the data is transferred using appropriate converters to interact with the control unit via the electrical interface. The environment model must have so-called real-time behavior, which means the response of the model must be guaranteed within the specified time constraint. That's the beauty of the hardware and loop simulation. This is to ensure realistic test so that the communication with the ECU is the same as in the real environment. Whenever I am referring the term ECU, that's the electronic controller unit, it can be when we are referring to the vehicle, it could be a body control module, it could be a ABS system, it could be a EBS, central body control unit, anything, or traction controller, or the battery controller, traction motor controller, anything. So the main goal of the HL testing is to verify the correct operation of the embedded software in the target processor and its surrounding components and the environment. When I refer the correct operation of the embedded software in the target processor means whatever the software is we have flashed into the ECU, we have to check its correct operations. And its surrounding components means whatever the sensors are connected to that ECU. If taking the example in the EMS, if you are feeding the crank and cam sensors input to the ECU, that is the engine management system ECU, we are able to simulate that, or we are able to using the real-time simulator, we have to simulate that and feed that input to the ECU. So we are fooling the ECU that it is actually connected to the real system. So this is what here also written by creating the virtual real-time environment that represent your physical system to control. Now, when we see the pictorial representation of the hardware and lip simulation, there are few points. The response from this HIL testing is a real-time response. This is highly accurate and results are close to the actual behavior of the system. Real-time application execution on the appropriate hardware platform. This is the key drive factor actually. So very simple. When it comes to hardware and in-loop simulation, you use a real-time simulator from the different suppliers. There are different suppliers or the different manufacturer in the market like Opal RT, National Instrument, or ITRAS. They produces the real-time simulator where you can simulate analog signals, digital signals, PWM signal, CAN signal, and this analog, digital, PWM in and out. Everything is possible. Even you can simulate CAN FD, CAN messages, everything you can simulate. But they are a real time. They simulate the real time signal with respect to time. You simulate that signal and feed that signal to the controller where your main logic is running. Again, this main controller is running on the target. When I say the target means your electronic control unit. Whatever the embedded code or the algorithm is running inside that ECU, you are feeding that signals. Just a best example of the body control unit. There we need to provide the input of your left indicator, right indicator, or any chime buzzer or any roop lamp. That all input goes to this body control ECU. If I talk about the engine management system, coolant temperature sensor or your crank cam pulse sensor or your manifold pressure information, everything which are simulated using this real-time simulator, all this information is fed to this ECU. And we are fooling actually this ECU saying that it is actually connected to the vehicle, but it is simulated in the environment with the real time, which feeds that signals to this analog, digital, PWM, CAN, all signals are fed to this ECU, and this ECU behave as a real as it is in the vehicle or it is in the one of the product. So that's the beauty of this hardware in loop simulation. Very simple, ECU and your real-time simulator. I'm going to talk more in detail about this hardware and loop simulation because in hardware and loop simulation, not only this real-time simulator and the ECU comes into picture, there are different parts of the hardware in loop simulation comes like breakout box, then fault insertion unit, then load box. So many major components are the major um, blocks presents important role in the HIL system. I'm gonna cover that more in details in my next knowledge sharing session in the next video. But today I am restricting here on just talking about the overview of the HIL. But I hope it is very much clear that when it comes to talk about this ECU and this real-time simulator, where we have to uh, prepare a simple model for your input and output signal. If you are modeling coolant temperature and it is a analog in the behavior, you have to simulate that using any software, as I mentioned, Simulink or MATLAB Simulink or NI LabVIEW or NI Veristand or AME Sim. That way you can simulate here and you run that model in on a real-time simulator. And for the ECU, that is everything which are inside the algorithm which runs on the actual ECU that is inside here. So in the pictorial presentation, if I see how the HIL system works, this is how it looks. Here is your actual ECU hardware, which gives some outputs which goes to your real-time simulator. Again, the real-time simulator simulate that analog, digital, PWM, CAN, any other signal that feeds whatever the signals required to make this ECU functional. All this gets simulated and fed here. But again, here host PC also plays very important role. You can generate the executable files and flash into the real-time executable files of your model, if you are simulating the coolant temperature, if you are simulating the battery model, if you are simulating the state of health, if you are simulating motor winding temperature, whatever you have simulated, you have to generate the executable file, flash that file into the real-time simulator. You have to map um, the card on which analog card pin or the digital card pin you want to generate that signal. Accordingly, you have to map that signal to the pin of that respective issue. I will cover more in detail about the HIL, but till now my focus was to bring you what is the SIL, what is MIL, and what is uh, HIL. So software in loop testing or software in loop simulation method, then model in loop simulation method, and the hardware in loop simulation method. Very high level when it comes to checking the performance of your code or finding out the bugs in your code. We usually prefer SIL, very fast, very effective way to find out the debugging or finding out the bugs in your code. SIL is widely used. When it comes to checking the entire logic which are written inside any of the ECU, then we usually use modern in-loop simulation technique. And when it comes to do the real-time performance, we usually prefer the hardware in-loop simulation. And this method is basically before production of that specific component. So this HIL is very, in terms of the fidelity, it's very high fidelity in terms of the results and very accurate in terms of giving the real-time behavior of that specific performance of the ECU or the performance of the model which we are simulating here. But before ending, I would like you to take through quickly on this product life cycle. Normally, this cycle is being used for development of the product, and we refer this as a V model. Sometimes we call it a V cycle as well. So this V model is a graphical representation of a system development lifecycle, and it is used to produce rigorous development lifecycle models and project management model. So this actually saves the time to bring the product or manufacture the product to the market. And it start from the requirement gathering, from the benchmarking as well as doing the research in the market. What product we want to bring? It start with the requirement, then it goes to system design, component design, software design, then it goes to ECU code building, then integration, calibration, and actual product development. So this cycle usually been followed everywhere when it comes to developing the new product. But very interesting part is that why I'm bringing this cycle here, V cycle here, or the V model. The reason is if you see this phase of this V cycle is called product definition. And here, when it comes to the component design, the MIL simulation is widely and extensively used. When it comes to software design, this SIL simulation testing method is widely used. And when it comes to the integration with the actual system and to look for the performance before going for the production, this HIL simulation comes into picture. MIL, SIL are being done with the one simulation or one tool. Here you need to have the different systems like real-time simulator, as well as you need host PC, as well as you need load box, fault insertion, you need breakout box, everything you need. But this method is very, very effective method to find out the real performance or to find out the accuracy of your system. So if you see the V cycle or the V model, which are the graphical representation of system development life cycle, on product definition, MIL and SIL is extensively used, and towards the product development, HIL is also used. So that's what I wanted to make sure that you guys would understand the impact of SIL simulation, MIL simulation, and the HIL simulation. So this is what I do have today for you guys. So thanks for watching my videos. I seen that I'm getting the good responses from the previous video as well. But before signing off, I gently request you, if you have not subscribed to my channel for more learnings for upcoming videos, please do subscribe. Please share this knowledge video or the knowledge session with your friends. Definitely they might need this information. So please share with them. And if you have not subscribed, please subscribe and don't forget to like. So thanks for watching the video and have a nice day. Bye bye.